Dear students, welcome back to Signals and System online video lecture series. In this class, I am going to talk about the orthogonality in signals. In the previous class, we have discussed the orthogonality of vectors. By reviewing the vectors, I am going to talk about the orthogonality concept in the signals. So, in the previous class, I have explained that all the signals are nothing but vectors only, because vector is nothing but it is a physical quantity which has the magnitude and the direction. If you see the signal also, signal can also have the magnitude and the direction, so that we can say that all the signals, basically all the signals are vectors. So first we are going to study some of the properties of the vectors. After that we are going to apply the same properties to the signals, because all the signals are vectors. In the previous class I have explained the 4 points of the vectors. One is dot product, another one is orthogonality in vectors. Orthogonality is nothing but statistically independent. Orthogonality can be defined at least between the two vectors. So if theta is not equals to 0, one vector is going to project one component on the another one, and while it is projecting any component C, it is going to define the another vector, that is called error vector, and finally by making all those things we can have the relation between those two vectors. So dot product we have discussed in the previous class. Dot product is nothing but, dot product can be denoted with a dot. Here we will be having the two vectors. Assume that two vectors we can call as f and x. I am assuming the two vectors which are f and x. Then the dot product of these two vectors is given by f dot x is equals to, we can call it as a dot product. F dot x is equals to, we can have this is modulus of f into modulus of x into cos theta. This is the dot product of the two vectors. If this theta is equals to 90 degrees, if the theta is equals to 90 degrees between the two vectors, theta is nothing but it is the angle between the two vectors. If it is 90 degrees, we can call them as they are mutually orthogonal vectors. Mutually orthogonal vectors. Here the point is very clear. If we have the two vectors, that is f and x, then the dot product of those signals is given by those vectors is given by f dot x is equals to modulus f into modulus x into cos theta, where theta is nothing but what? It is the angle between the two vectors. Angle between the two vectors. For our convenience, assume that this is f and this is x. So now the angle between these two is equals to theta, and if this theta is equals to 90 degree, if this theta is equals to 90 degrees, then we can have the vector x is like this and vector f is like this, because the theta is equals to 90 degrees. If the theta if the angle between the two vectors is equals to 90 degrees, then those two vectors we can call them as mutually orthogonal vectors. Mutually orthogonal means what? Statistically independent of one on another. That means what? Here this is a vector, it is having the magnitude and the direction, and x is also one more vector. This is a x is also one more vector, it is having the magnitude and direction, so that these are having the angle between them is equals to 90 degrees, so that here this f is statistically independent on x and this x is statistically independent on f, so that orthogonality is nothing but statistically independent on one another. So that orthogonality is nothing but when the two vectors, the angle between the two vectors is equals to 90 degrees, so that one vector is statistically independent on the another vector, so that we can call those two vectors are orthogonal vectors, mutually orthogonal vectors. If this theta is equals to 90 degrees, for example, if I am going with the condition that is theta is not equals to 90 degrees, but it is less than 90 degrees, that means that we can have this case. Theta, we are saying that when the theta is equals to 90 degrees, those the two vectors are orthogonal vectors, but we are saying that theta is not equals to 90 degrees, it is less than 90, in that cases we can have this one. When the theta is less than 90 degrees, the angle between the two vectors is less than 90 degrees, we can have the projection of one vector along another. Projection of one vector along another, so that due to the theta is less than 90 degrees, then one vector will define, one vector will project one component along another vector, and that component is denoted with C. For example, this is a f, this is a f, it is one vector. Due to the theta is less than 90 degrees, so that it is going to define, it is going to project one component along x, so that we can call that is component is Cx. C is a component, and C is a component which is projected by the vector f along the x, and so that it is going to define, when it is going to project one particular component along the x, it is going to define one vector. That vector is also called as error vector. Error vector, it is denoted with E, and it is a C is a component. When the theta is equals to 90 degrees, we can call them as orthogonal vectors. When the theta is less than 90 degrees, one vector will project the component along the another vector, so that that component is C. In this case, we can have that C is a component along x, so that the relation between the two vectors when the theta is less than 90 degrees, when the theta is equals to 90 degrees, this C is equals to 0. That means what? It will not project any component along the x. When the theta is less than 90 degrees, when the theta is less than 90 degrees, we can have the relation between the f and x. F is equals to, this is C, and x, this is a vector plus E. That means what? F is a vector, f is a vector, and x is also vector. Due to the theta is less than 90 degrees, theta is less than 90 degree, this vector f projected one component along x, and due to that one we have the error vector also. This point, all these points I have explained in the previous class. This is what? All these things at theta is less than 0, less than less than 90 degrees. If theta is equals to 90 degrees, what is the case now? Theta is equals to 90 degrees means dot product is equals to 0. First point, theta is equals to 90 degrees. The angle between the two vectors is equals to 90 degrees. So that f dot x is nothing but it is a dot product is equals to 0, because cos 90 is 0. Then if theta is equals to 90 degrees, we can call them both the signals are orthogonal signals. If both the signals are orthogonal and these are angle between them is 90 degrees, so that f will not define, or f will not project any component on x, or x will not project any component on f, so that component C is equals to 0. If component C is equals to 0, their error vector is also 0. This is the case when the two vectors are orthogonal to each other. Now we have to apply all these concepts to study the orthogonality in signal, because this we have studied the orthogonality we have studied in the case of vectors, because if you go with the signals also, all the signals are basically vectors only, so that we can apply this orthogonality concept in case of signals. Now I am going to apply. Now I am going to apply the concept of orthogonality. Concept of orthogonality in signals now. The concept of vector comparison and the orthogonality can be extended to the signals. Let's consider the two signals. F of t is one signal, x of t is another signal, then E of t is the error signal. Then substitute this in this equation, so that what we can have this from this vector equations, that is f bar is equals to cx bar plus E. So that here in place of f vector we took the f of t signal, in place of x vector we took the x of t is a signal, and here E is a error vector, but we can consider in case of signals it is a error signal. Now we can form the equation for this one. What is that? F of t is a continuous time signal is equals to c into x of t plus E of t. From this, error signal is equals to what? Error signal is equals to, we can write error signal is equals to, we can write f of t minus c into x of t. This is the error signal equation. This is the error signal equation. F of t is equals to c into x of t plus e to the e of t. Then we can have this limits for this one is E of t is nothing but what? It is the error signal. E of t is equals to f of t minus c into x of t. Limits for this one is from t1 less than or is equals to t less than or is equals to t2. Otherwise, it will be the 0. This is the limits for the error signal. Error signal we have defined from the two signals, and we have adopted that concept from the vectors. So that now if I go with the squaring of this signal, that means what? We can have, we know the minimum value of E of t will be best approximation of f of t in x of t. The minimum value can be obtained by minimizing the minimum mean square value of E, which is nothing but energy of E of t over the internal T1 and T2. We know that in the last, in the first unit, we have studied the energy signal. Energy signal is nothing but squaring of any signal is nothing but energy signal. Now I am going to find the energy signal. Now I am going to find the energy signal of error signal, that I can call it is of energy signal. I can call this is EE. EE is equals to limits. We know that integral T1 to T2, squaring of any signal will be error signal, and we are going to calculate energy of error signal, that is E square of t dt. Then we can have EE, that is nothing but what? Energy of error signal is equals to integral T1 to T2. T1 to T2, we know that what? E of t is equals to f of t minus c into x of t and dt. This is square now, because what? E square of t is nothing but it is the energy of the error signal. The value of E, this value of E depends on how we choose c. Value of E depends on how we choose the value of c, and we have to choose the value of c such that cx of t gives the best approximation of f of t. So that what we have to do, then we have to go with the we have to go with the, we have to differentiate E with respect to the c and equate to 0. That is nothing but what? We have to go with the best approximation. That is nothing but the value of E depends on how we choose c. We have to choose the value of c such that cx of t gives the best approximation of f of t. So that what we are doing, we are doing the differentiation. We are doing the differentiation on the EE, that is energy signal with respect to the c, so that it will be equals to 0. Because what? When the two signals are said to be orthogonal, when the two signals are said to be orthogonal, c is equals to 0. In case of when the two vectors are said to be orthogonal, c must be 0, and we are equating that to 0. So that here what we are doing now, we are going with the differentiation of E by with respect to the d c is equals to d by dc of we know that integral this EE, we know that this is the part of EE, integral T1 to T2 f of t minus c into x of t, and this is square now, square into dt now. Now you can equate to this is 0 because we have the equation. So that what we can have now, from this we can have, and it is a plus b whole square, so that I can directly write this is d by dc of integral t1 to t2 a minus b whole square is equals to a square minus 2ab plus b square. So that a square is this one, integral t1 to t2, that is f square of t dt minus 2ab, 2 is nothing but this is 2, and a is nothing but integral t1 to t2, that is what, f of t into f of t, 2ab, b is nothing but this one, and c is a constant, we can call it here, right, and into x of t into dt plus a minus b is equals to a square minus 2ab plus b square is this one, and c is a constant here, integral my c square integral t1 to t2 and x square of t dt is equals to what, we have a 0. Now we are going to have the here the first integral. The first integral is independent of c, then it is equals to 0, and here the differentiating remaining two integrals, we get this is about the integral c. Here see this one, we can apply the integration, see this one, this is we can apply d by dc of integral t1 to t2 f square of t dt, and d by dc of 2c integral t1 to t2. Like this, if you apply the differentiation to the three terms, and so that we can get that is equals to what we can get now, we can get it is minus 2 integral t1 to t2 f of t into x of t, this is minus 2ab term plus dt plus 2c, because we differentiated the c square with respect to the c, so that 2c integral t1 to t2 x square of t and dt, because first term is not having any c, so that we can have that integration of constant will differentiation of constant will be 0, so that we can have this is 0 now. Now what I can do this is what? Now I can do this is if I go with here, if I am writing this is 2c integral t1 to t2 x square of t into dt is equals to, I can write this is equals to right hand side 2 into integral t1 to t2 f of t into x of t dt now. So that 2 to get cancelled we can have, then from this I can write c is equals to what I can write, c is equals to, we can write this as integral, we can write integral t1 to t2 f of t into x of t dt by integral t1 to t2 x square of t dt. If you observe clearly, if you clearly observe the denominator is nothing but squaring of a signal. Squaring of a signal is nothing but this is what it is, energy of a signal. This is nothing but energy of a signal. Energy will not be 0. Energy will not be 0. So that to make c is equals to 0, this energy is not equals to 0 because it is an energy signal. So that obviously this part has to be 0. That is what? To make c is equals to 0. To have the c is equals to 0, obviously integral t1 to t2 f of t into x of t dt. That means what? What is the condition? When the two signals are said to be orthogonal. When the two signals are said to be orthogonal, the condition is what? The c must be 0. C must be 0 to have the orthogonality between the two signals. c must be 0. To prove the c must be 0, what we have to prove? That is integral t1 to t2 f of t is a one signal, x of t is another signal, dt is equals to 0. If we prove integral t1 to t2 f of t into x of t dt is equals to 0, we can say that the given x of t and f of t both are orthogonal to each other. Here we try to find out c is nothing but component. When the two vectors are said to be orthogonal, that is theta is equals to 90 degrees. If the theta is equals to 90 degrees, c will be 0 and c will be 0, and we have adapted that from the vector, so that c is equals to 0 means we have the equation c is equals to this one, and in order to make c is equals to 0, this denominator will not be 0 because it is a energy signal. Energy will not be a 0, so that it is nothing but to make c is equals to obviously 0 by energy, it will be the 0 only, so that numerator has to be equal to 0. Numerator is what? Numerator is integral t1 to t2 f of t into x of t dt is equals to 0. If we prove integral f of t into x of t dt is equals to 0, we can say that the given two signals, that is f of t and x of t, are the orthogonal to each other. The denominator of the above equation is the energy of the signal, and the above equation is similar to the we have studied in the vectors analysis, and in the equation the denominator represents the x of t, it can't be 0, hence the numerator must be 0 to make c is equals to 0. If c is equals to 0, there will be no component of f of t along x of t, then x of t and f of t are said to be orthogonal and interval t1 to t2. For the orthogonality, what is the condition? Integral t1 to t2 f of t into x of t dt is equals to 0. This is the condition. By making use of this equation, we have to solve some of the problem. So I am going to conclude this session. Vectors and